Hey guys, welcome back to my channel camnotion.com. So as we are discussing the Get Chemistry Question Paper 2019, as you can see, this is part 8 presented by me Amarjeet. And guys, I request you to subscribe to my channel, and if you like my explanations, give a thumbs up to this video, and let's begin this video. Right. So here we have first question: the correct order of basic strength of the following metal hydroxides. Right. These are metal hydroxides belongs to first group, and we know that down the group, basic strength increases and acidic strength decreases. Right. Acidic strength will be decreased and basic strength will increases. uh, so from this, cesium hydroxide will be the most acidic, or you can say it is the basic strength will be more, and lithium hydroxide, which is acidic, which is most acidic. Right. So that means, for this question, option C will be the right option. Cesium hydroxide will have a most basic strength, then potassium hydroxide, then sodium hydroxide, then lithium hydroxides. Right. So moving to next question. The correct order of carbonyl stretching values for the following order of compounds. Like, so correct order of C11O bond stretching. Right. Since we know that bond stretching, which is any bond, but bond stretching is frequency is directly proportional to, that is, let's take here VCO, that is carbonyl bond frequency, which is directly proportional to its bond order. Right. So as the bond becomes stronger and stronger, its stretching frequency increases. Right. Therefore, so when the carbonyl is in its free gaseous state, it will have a most, or you can say more stretching values. Right. For then when it is attached in any compound, then it is attached with metal atom through carbon. Here, this metal atom have non-bonding electrons, which it can donate to MC bond, and this increases the MC bond order. This increases the MC bond order, and as well as it decreases the CO bond order. Right. So the thing is that, so when the metal atom have available non-bonding electrons, it can donate this electron to MC bond order, which MC bond, which increases the MC bond order and as well as decreases the C11O, that is CO bond order. Therefore, in options we have vanadium CO6, chromium CO6. Now in chromium CO6, chromium is in zero oxidation state, and vanadium CO6 minus, here vanadium is in -1 oxidation state, and Mn CO6 plus, where Mn is in plus oxidation state. Right. Now vanadium, which is in minus oxidation state, that means it will have so it can easily, it donates its electron pair to MC bond order, and in this compound, that is vanadium CO6 minus, the C11O bond order will be least, that is it will have a lower value of carbonyl stretching values. Right. So vanadium, in vanadium CO6, since C11O bond has least bond order, and therefore its stretching values will be lower in this compound. Then CO6, which is in zero oxidation state, will have next to VCO6 minus, and Mn positive. Since it is a positive species, so it do not have sufficient electrons which it can donate to MC bond order, and as well, and consequently CO bond order cannot decrease, right? So in this compound, that is MnCO6 plus, the CO stretching value will be highest. So from this we can get to know that MnCO6 plus will have more stretch in this compound. Carbonyl have more stretching values than CrCO6 than VCO6, right? For this question, option D is the right option. And when C double bond, or that is carbonyl in its free state, always have a highest stretching value, right? For this question, option D is the right option. So moving to next question, the correct order of bond angles of phosphorus trihalides, right? Phosphorus trihalides. Now here, in case of phosphorus trihalides, the bond angles is basically due to the bond pair repulsions. So when the bond pairs are close to each other, they will have more repulsion and will causes more or you can say increase in bond angles, right? So which will only be determined by the atom which is attached with the phosphorus, right? So when it is when phosphorus is attached with the when fluorine is attached with the phosphorus, then the bond pair, since fluorine is highest electronegative element, therefore a bond pair will shifted towards fluorine atom and will have a least repulsion, and which causes a decrease in a bond angles, right? This compound will have least bond angles, and since bond pair is moved to towards fluorine atom, therefore in this compound, that is PF3, will have least bond angles, right? So and when iodine is attached with this compound, since iodine is least electronegative element among halides, right? So iodine will have in this compound, the bond pair will not shifted much towards a halide group. That is, bond pair will be there in will be in a closer state, so it will cause more repulsion. And for in the compound Pi3, will have the IPI bond angle will be maximum, right? So Pi3 will have maximum bond angles, and then PBr3, then PCl3, then PF3, right? For this question, option C is the right option, right? The product of C2x sigma xy, where C2x is the two-fold rotational axis around x-axis and sigma xy is the xy mirror plane, right? Since C2 is the is an principal axis, or you can say two-folded rotation is there, we can consider water molecule which have a C2 axis of rotation, right? So since xy plane is there, since xy plane is there, and this is z, since this plane is bisecting the molecule in such a way that it is a sigma plane, right? Now the another sigma plane will be there in the compound is sigma z, but yz cannot is not possible because it will not bisect the molecule, right? It will cannot bisect the molecule because it is not a planar molecule, and the another sigma plane will be xz. So option for this question, option A will be the right option, since we know c C2 sigma is equals to sigma dash, right? This is a group multiplication. This is from group multiplications assumptions, right? For this question, option A will be the right option, sigma xz, right? So moving to next question. So here you can see a compound X and Y atoms has a X and Y has a cubic unit cell, right? They are in a cubic unit cell, and X atoms are at the corners and the body centered position. So X atoms lies in the corners and also in the body centered positions, and Y are at the face center positions of the cube. Y present at the face center positions, right? The molecular formula of the compound, right? These are the options. And this, since this is a numerical base, so I have also written the solution for this, right? Since X atom present at the corners, so contribution per corner is always 1 by 8, which we know about this. So therefore 8 corners are there in a cubic cell, that is 8 into 1 by 8, which will give 1 atom per unit cell. That is, when any atom present at corners, then it will contribute 1 atom towards per unit cell, right? Also X atom also present at body center, therefore the body center means it is present at the middle of the cube. So it will also contribute 1 atom per unit cell. That is, uh, X atom will contribute total of 2 atom per unit cell. That is, per cubic unit cell there are 2 X atoms are present. And also here Y atoms are at face centers. Now we know that in a cubic unit cell there are 6 faces, and each faces there we need to one atom contributes half for each unit cell, right? There since 6 uh, faces are there, and contribution of per face is 1 by 2, therefore total of 3 atoms per unit cell are there in the cubic unit cell. So total number of Y atoms are there in the per unit cell is 3 atom, therefore the formula will be X2Y3, right? X2Y3. Now moving back to options. So option A, here option A is given as X2Y3. So for this question, option 2 will be the right option. Moving to next question. Uh, 2 mole of CO2, 2 mole of N2, and 4 moles of oxygen mixed at 300 Kelvin. The entropy of mixing is. This is a question from Dallas mixing, that is entropy of mixing, right? So these are the options. Also I have written the solutions for it, for this question. Now see, since we can assume n1 is equals to 2 mole, n2 is equals to 2 mole, and n3 is equals to 4 mole, which is here as you can see, CO2 is present at 2 mole, and nitrogen is present as 2 mole, and 4 moles of oxygens are there. Therefore we can write n1 is equals to 2 mole, n2 is equals to 2 mole, and n3 is equals to 4 mole. Now from the you should know the formula for Dallas mixing, which is this: minus R summation of Ni ln xi, right? Summation of Ni ln xi. What is xi? It is the mole fraction, right? So we can determine mole fraction for carbon dioxide, which is equals to moles present, total number of moles present, that carbon dioxide present, and by total moles mixture of the gases, right? Which gives 1 by 4. For N2 it is 1 by 4, and for X3 it is, that is for oxygen it is 1 by 2. The mole fraction for oxygen is 1 by 2. Now putting these values in the equation, this is the equation, since it is a summation of ny L1 x1 plus n2 ln x2 plus n3 ln x3. So if you put these values, that is n1, n2 and n3 values, and these equations, you will get R into 8.292, right? But in the options, if you go through the options, you can there is ln2 is present in each of the options, right? So we can divide this term by ln2. We can divide this by ln2, then we will get 11.96 r ln2, right? which is approximately equals to 12 ln2, which is approximately equals to 12 ln2, right? So this 8, so we can convert it to ln2 for form by dividing the r into 8.292 by ln2. Then we will get 12 r ln2 as a solutions, right? So for this question, right option is 12 r ln2, that is C is the right option for this question. Moving to next questions, the eigenvalue corresponding form of eigenfunctions of a Hamiltonian operator must be positive, negative, imaginary, or real. So we know it is a real value always, right? Moving to next question. The half-life of a zero-order reactions, that is A goes to product, is given by. So the integrated rate equation for zero-order reaction, we can write x is equals to k naught t, right? This is the integrated rate equation for zero order reaction, where x is the product concentration at time t, and cannot represents a rate constant for zero order reactions. So when so at half life period, we can write t is equals to t half, right? And from this equation it will be and x at half life period, x is what? It is the product concentration, that is at half life period it is the 50% reaction goes to product, right? 50% of reactant concentration converted to product concentration, that is instead of x we can write a naught by 2 here, right? So instead of x we can write a naught by 2 here, and it is k naught, right? So if you solve this, you will get t half equals to a naught by 2k, right? K naught. So therefore this a naught, where a naught is the reactant, initial reactant concentration, right, when time is 0. So half life of a zero order reaction can be given as t half equals to a naught by 2k naught, right? For this question, option D will be the right option. So guys, I hope you like this video. If you like my explanation, give a thumbs up to this video, and thanks for watching.